So here we want to look at our hydrogen nucleophiles. So these get a little bit tricky to deal with. So if we were going to look at our standard definition for nucleophile, it needs to be electron donor. So we would need electrons. Easiest way to make a hydrogen nucleophile then would be to say H-, and we just do hydride. We have seen hydride show up this semester. We saw it when we looked at our stupidly strong bases, say something like sodium hydride. So that would be a nice, easy way to get it kind of into solution. Now we've got hydride. The problem with that is that it is incredibly reactive. So much so that if we take sodium hydride and try to put it into an organic solution, what ends up happening instead is it stays a solid. So we would have our solvent floating around, and we'd have this solid at the bottom preventing it from dissolving, which means that sodium hydride becomes very, very sterically hindered, and that can be a bit challenging to deal with because what that's going to mean is that it can only act as a base, not as a nucleophile. So we need some other way to manipulate and control the presence of that hydride so that it can act as a nucleophile. And that is really going to come in when we throw in our boron and aluminum group elements. And so when we look at boron, if we said, say, BH3, and we're asked to draw out a Lewis structure, hopefully what you would get to would be something along these lines. And we wouldn't have any more electrons. So we might say that boron doesn't have its octet. We can't draw more electrons in because we've shown all of our electrons. Okay, so that ends up being its Lewis structure. Well, the real question then comes out of this is, what is the hybridization? Well, the hybridization then of that boron is going to be sp2. There'll be a leftover empty p orbital. Well, that empty p orbital could accept electrons. What electrons could it accept? It could accept electrons from a hydride. And there's our nucleophilic hydride, which could really help us out as far as the reaction goes. And that's kind of cool. Okay? So if we continue that on, we're really seeing two different ways that we can get the hydride. We can either get it from sodium borohydride or the same aluminum hydride. Both boron and aluminum, being in the same column of the periodic table, have the same chemistry associated with them, and that's that empty p orbital that we can place those electrons. And so when you see those reagents, you should really just be zeroing in on the fact that we have a nucleophilic hydrogen. The boron and the aluminum are really there to kind of stabilize it and allow it to act as a nucleophile instead of as a base. Okay, so those are the two big reagents. So let's push this a little bit further and say, well, why do we have two reagents? What are the differences between them? And if we go through and look at this, hopefully what we see is, first off, it's sodium versus lithium. And then we might also see that we're looking at aluminum versus boron. Okay? And trying to key in on those differences could be helpful. The next thing that you might note as a difference is that this is all done as one step, and this is being shown as two steps. Okay, so there are some pretty big differences as far as the reactivity between these go, okay? And that's what makes this interesting. So why do we need that difference? Well, that difference is also going to come down to a concept known as selectivity. Right? Each of these reagents will react differently in different scenarios and thus force a different selectivity behind it. Okay, so why these differences? Well, let's go through and take a look at the Lewis structures. They're both sp2 hybridized with that empty p orbital. Why would we get kind of a difference in reactivity? Well, the first thing let's go through and do is let's take a look at the kind of core element, our aluminum versus our boron. And this drawing kind of hides some interesting features. Aluminum is lower on the periodic table, and because it is lower, it is actually larger. Right? So the bond length between the aluminum and the hydrogen is significantly longer than the bond length between the boron and the hydrogen. Okay? Well, the shorter that bond is, the stronger it is. So as soon as we move to aluminum, we've now made this hydrogen more reactive because it is floating further, it is further from our core element. Okay? So that makes it more reactive. So we're looking at kind of a bond length argument. You could also look at differences in electronegativity that can kind of contribute to this, but the size is going to be our larger definer. Okay? Let's push this a little bit further. We move out to the next big difference that we pointed out. We have lithium versus sodium. Both of those are alkali metals, and we might think, as in most cases, they don't really do much. And they kind of don't, but they are able to help polarize a structure, say like our carbonyl. That carbonyl could polarize out to having a negative oxygen and that positive carbon. If we go through and look at the difference in reactivity between, say, our lithium and our sodium, the lithium is smaller than our sodium, which is larger. Okay, well, how does that affect things? The larger, we said, made it more reactive. So this seems to be kind of a counteracting system, except where's that larger and smaller interacting? Well, they're both positive. They're actually interacting with the oxygen in our carbonyl. Showing a dotted line there was a bad idea. And if we did lithium, that ends up being a shorter bond, so that polarizes the carbonyl really, really well. If we went out and did, say, sodium, being a longer bond, that bond is weaker, it's polarized less. So because the lithium is smaller, it actually polarizes the carbonyl more, making it more reactive. Okay? So in the cases that we just looked at, looking at the center element and then that kind of vestigial counterion, both of those pieces contribute to lithium aluminum hydride being more reactive than sodium borohydride, and that bears out. Okay? How do we see that bear out, or bear witness to that, I guess? Well, that's the last thing we pointed out. The lithium aluminum hydride required 2 steps, whereas the sodium borohydride could do it all at once. Any way you run this, we need that hydride to come in and attack, and then we need to place a hydrogen on that oxygen to neutralize that charge. In the case of sodium borohydride, both hydrogens come in at the exact same mixture, or in the same mixture. With the lithium aluminum hydride, they're coming in as separate steps. Well, why might that be the case? Okay. Well, what's the reactivity of those hydrogens? So let's erase that and draw out our reaction. Remember, the whole point was the hydride comes in, tacks down there, and we would have another hydrogen up there. So we really have 2 hydrogens. We'll call them a red and a blue. The red one was what drove this. That was our nucleophile, sodium borohydride. There it is. And then our blue one comes from our water. If we go through and look at the lithium aluminum hydride, same deal as far as the pairing goes. Okay? In both cases, our red hydrogen's coming in first as the nucleophilic one. The blue hydrogen comes in secondarily. Well, what is the charge on that hydrogen? What charge does it come in? Okay, well, if we think through our mechanism, hydride came in as a negative, causing the pi bond to break, which gave us our carbon with the hydrogen, and then a negatively charged oxygen. For that negatively charged oxygen to react with a hydrogen, that hydrogen has to come in as a positive to get that blue hydrogen on. So the chemistry has to change. Why might that be problematic? Well, what would a positive hydrogen be attracted to? A negative, yes. A negative oxygen or a negative hydrogen. Okay, because the hydrogen is theoretically more reactive, or the hydride more reactive, we might expect that reaction to happen before the nucleophilic attack. Sodium borohydride's hydride reactivity is so low that it won't react in large amounts with the positive hydrogen from our water. Lithium aluminum hydride, however, that hydride is now so reactive that it would react with water, right? Thereby quenching the hydride reagent, and we wouldn't get the nucleophilic attack. That's why we have to separate the two hydrogen reactions with lithium aluminum hydride. Sodium borohydride we run as one. Right? So the reactivity imbalance behind those is what's allowing those reactions to happen either in those particular patterns. Okay? So reagent conditions and solvent choice. Sodium borohydride, relatively mild, not a big deal. Our solvent choice can be anything because the sodium the boron will stabilize that hydride enough, and the sodium will polarize the carbonyl enough that we can do that as a relatively mild condition. So I can use any solvent I want, and I can run it as one pot. Lithium aluminum hydride, though, with the aluminum making that hydride more reactive and the lithium making the carbonyl more reactive, that we end up seeing some conditions matter here. And in this case, that condition means the solvent can't be protic. It can't have that positive hydrogen in it, and it needs to be a solvent like ether to limit that reactivity. Okay? And so what we see is really just solvent choice. Sodium borohydride, use whatever you want. Lithium aluminum hydride, you have to split it in two steps, and you have to make sure that there's no acidic hydrogens in your environment. Where can you find those acidic hydrogens? Well, as the diagram below is showing, that would be an alcohol. Okay? With sodium borohydride, that reaction is so slow that we don't really have to worry about it. With lithium aluminum hydride, it's incredibly fast. You will actively see hydrogen gas bubble off of that. That becomes problematic because hydrogen gas is flammable and explosive. Okay? So what does that mean for our overall reactions? Okay, well, if we look, we've got a smattering of different carbonyls, right, polar pi bonds that could potentially react. Okay? Sodium borohydride is a less reactive hydride source, which means it doesn't react with all polar pi bonds. The lithium aluminum hydride, however, is incredibly reactive, and so it does react with all of them. Okay, so we can see some limitations behind the individual reagents. At this stage, we aren't going to push it too much further, okay, to really nuance the difference between those, because the nuancing really comes in with this structure, which is known as an acid derivative. We end up changing kind of the functionality that we now have what we could classify as a leaving group connected to the structure. If we look at the rest of those examples, none of those are leaving groups, and so it doesn't really change our chemistry too much. With a chloride, the leaving group does change it, and we'll see that in chapter 20 and 21, and that's when we'll see a really big difference between the lithium aluminum hydride and the sodium borohydride. At this stage, really all you need to be concerned about is that your nitriles, which is that cyano group at the end, will react with lithium aluminum hydride, but our sodium borohydride will not, so we get a selectivity there. Okay. And that our lithium aluminum hydride needs to run in two steps with an aprotic solvent. Okay. If you're unfamiliar with the protic term, you might need to go back and look at the solvent review videos that were addressed earlier in the semester. I'll try and link it in the description. So this is really going to set us up for that preview in chapter 20. Okay, again, if we go through and look at these functional groups, we're starting with the ketone. There's really no leaving group. We then move to an ester. The ester is different because this could leave the structure. We get a negative oxygen, okay, as a leaving group. And in the last case, we get the chloride. The chloride's a great leaving group. So that leaving group ability is really going to differentiate our reactivity between our lithium aluminum hydride and our sodium borohydride. Okay, so don't stress about those yet. Just realize they are going to show up. You might play around with it, react it with a hydride, see what happens, take a guess at what you would expect to happen, and see what happens. So that a lot. The last thing we've got here is just some practice. So this is where I would ask that you go through and pause the lecture video again. You hit the space bar, click, do whatever you got to do, pause the lecture, and attempt these questions. Did you pause it? Did you get your answers? Okay, let's take a look. So if we start this off, we take a look at that very first one. We see the lithium aluminum hydride and we go, oh, lithium aluminum hydride. That's just going to add our hydrogen to it. Okay, and we could get our answer. Okay, one of the things that you may note or need to be aware of is that you will see these on multiple choice exams, and it is rare for you to ever see it drawn that way. You would very likely see it drawn this way, where that hydrogen became implied. Okay? For those of you screaming, but wait, I thought, we move to the very next question. The next question is the exact same reagent. So what did I miss? So if we backtrack, what we should note is that the second one has 2 steps, and the first one only did it as 1 step. What does that mean? Well, that means that I screwed up. Okay? How did I screw up? The second one is following the appropriate pattern. Lithium aluminum hydride needs 2 steps. That's where we're going to end with our alcohol. And in that very first one, because we're doing it as 1 step, we're not getting the alcohol. So let's switch this to a multiple choice format. You could potentially see this show up as your answers. And we'll be extra tricky here. Because that's all I've got at this point. Okay. So there you go. 4 answers. What is it? Hopefully you would acknowledge that you can't entirely remove the oxygen, the carbonyl, with hydride. We'll address how to do that much later in the semester. Okay. And you should hopefully also recognize that because we did not do it in 2 steps, that D is not a valid answer. Okay. Well, then what should the answer be? C or B? I would argue it's actually both of them. Okay. A bit misleading. Okay. The carbonyl won't react because the lithium aluminum hydride is going to react with the HCl instead. When it reacts with the HCl, we are getting H- with H+. That makes H2. Okay? So in a multiple choice test, you could see the quote-unquote desired product, okay, that you would have predicted from that reaction, and then they'll probably also subtly throw in there the starting structure, and you'll be like, well, why would you do that? And you'll try and eliminate that right away. If you see the starting structure, you should pause, and you should really critically evaluate, should that reaction have happened. Okay? And then with the last 2, we're moving to sodium borohydride. All we're doing is adding hydrogen to the polar pi bond. We would get our alcohol. If we really wanted to specify that extra hydrogen, we could show it in there. If you draw it like this, our online homework system will yell at you. The instant you specify 1 hydrogen connected to a carbon, you must specify them all. Well, where did that green hydrogen come from? That green hydrogen started on the structure. Okay? So be careful with aldehydes. It's super common to delete hydrogens with aldehydes. So be aware that they are present. The last one gets a little bit trickier because in the last case, we're being asked for what is the starting material. So you would have to reverse this process. Okay? You'd have to acknowledge that sodium borohydride gives us an H-. Okay? So looking at our final product, where's the easiest place to place an H-? This H would be an H plus because it's next to an oxygen, so that doesn't make sense. But that oxygen being electronegative is going to pull electron density away from that carbon, making that carbon quite positive, which could mean it was susceptible for a nucleophilic attack. Okay? So if we're looking for that polarity, that could help tip us off that what we're looking at for our final or our starting structure is that that oxygen is pulling electron density away, but I need a hydrogen to be able to form a bond. So I need to break a bond. There's that pi bond that I would need. That polarization is what's allowing for the hydride attack, and we now have our potential starting material. Okay? So use the information that you have in front of you, look at differences in electronegativity to help kind of predict where that reactivity is going to fall. One of the things that I did not discuss at all in these slides is that our lithium aluminum hydride and our sodium borohydride are incredibly common reducing agents. Okay, and they're reducing because we've lost an oxygen bond. Okay, we've replaced it with hydrogen. Okay, so you should remember that from OChem 1. If you got questions about it, you can always ask me and I can respin that reduction and oxidation video. This is really being split into kind of 4 pieces. Interestingly enough, there is lithium borohydride. There is also sodium aluminum hydride. Okay, there are a variety of ways that you can kind of mix and match these pieces. So what we've now addressed is lithium aluminum hydride, lithium borohydride, and sodium borohydride and sodium aluminum hydride. But we could also go through and say, well, how about sodium borohydride dicyano? And really what we're trying to key in on is that that boron-hydrogen bond is the critical bond, and those cyano groups are now modulating the boron chemistry. Why is that important? Well, if I want something that is selective, say to reduce an ester or to reduce a carbonyl in a particular place but not in another, I can modify those external pieces to change the chemistry just enough that the chemistry that I want to happen occurs. This becomes tricky for you because we now get almost an infinite amount of ways that we could change out this reagent. But what you need to do is focus on where the chemistry is. It's that boron-hydrogen bond. Okay? That's what's making that hydride so incredibly reactive. The rest of it is kind of superfluous information. The same thing with the aluminum and hydrogen. Okay? So focus where the chemistry is. We're concerned about that borane column with hydrogen. That's getting us our reducing agent. Okay? With that, we're done with our hydrogen nucleophiles. And I stopped the wrong video. Okay? So we'll pick up with our carbon nucleophiles in the next sequence.